Because of the nature of the field, elastic and electromagnetic equations are written in terms of vector calculus. Though this is hard for the novice to begin with, the notation rapidly becomes a useful, not to say essential, tool of the trade in elastic and electromagnetic theories. This review provides you with an opportunity to familiarize you with vector calculus and notation. Anyway, this lecture is an important resource as you go through advanced energy solutions. You may need to visit these materials regularly until you master these definitions and notation. Some of the key outcomes are to familiarize yourself with the physical meaning of divergence and curl, and the usefulness of both the integral and differential forms of each equation. Familiarize yourself with the notion of Kronecker and Levi-Civita tensors. These two tensors are important for elastic and electromagnetic studies. Familiarize yourself with Summation Convention. Start with the review of scalar, vector, and tensor fields. Let's define the coordinate systems that will be used in this lecture. A coordinate system defines a set of 3 reference directions at each and every point in space. The origin of the coordinate system is the reference point relative to which we locate every other point in space. A position vector defines the position of a point in space relative to the origin. These 3 reference directions are referred to as coordinate directions and are usually taken to be mutually perpendicular or orthogonal. Unit vectors along the coordinate directions are referred to as base vectors. In any of the orthogonal coordinate systems, an arbitrary vector can be expressed in terms of a superposition of the 3 base vectors. Such a coordinate system is called right-handed. Note that the base vectors can, in general, point in different directions at different points in space. Obviously, if they are to serve as references, then their directions must be known a priori for each and every point in space. In this class, we shall solve problems using Cartesian orthogonal right-handed coordinate systems. The base vectors are I1, I2, and I3. The position in this configuration is specified by the vector. X in bold, which represents the vector here, equals XYZ, equals X1, X2, X3. A scalar is a quantity having only an amplitude and phase, for example, temperature and charge. A vector is a quantity having direction in addition to amplitude and phase, for example, displacement and force. A tensor is a quantity represented by a multidimensional array of values. The rank, or order, or degree is needed to describe a tensor. A scalar is a 0-rank tensor, and a vector is a 1-rank tensor. A field is a spatial distribution of a quantity. In general, it can be either scalar or vector in nature. Note that in elastic and electromagnetic theories, the scalar and vector fields are in general a function of x, y, z, and t. That is, they are functions of position and time. The simplest physical field is a scalar field. By a scalar field, we mean a field which is characterized at each point or position by a single number, a scalar. The number may change with position and time. As an example of a scalar field, let's consider a pressure field in the water column during a seismic experiment. The pressure varies with x, y, and z. It also varies with time. Pressure P, x, y, z, t is a scalar field. There are also vector fields. In this case, a vector is given for each point in space. As an example, consider the motion of the ground during an earthquake experiment. The displacement of the ground at any point is a three-component vector, which is a function of position and time. Here is an example of a vector field. Each point of the medium is described by a vector. There are also tonsorial fields. In this case, a tensor is given for each point in space. As examples, consider the motion of the solid Earth during an earthquake. The strains, or deformations of the rock formation, and stresses, or forces on rock formations, are described as second-order tensors, and the stiffnesses of the rock formation, that is, the resistance of rock formation to deformation, as a four-order tensor. Let's now review the notions of scalar product, gradient, and divergence. The product of two vectors can be either a scalar or a vector. For cases in which the product is a scalar, it is referred to as a scalar product, inner product, or dot product. Let us consider these two. Notice that the dot product between two vectors give a scalar result. Simple trigonometry may then be used to show that the scalar product can be written as the magnitude of vector A times the magnitude of vector B times cosine theta. Theta is the angle between vectors A and B. Note that here, vectors A and B differ in direction by angle theta, as shown here. The projection of A onto B is magnitude of A times cosine theta, as shown here. Multiplying this projection by the magnitude of B gives the scalar product. The notion of the unit normal vector is also important in elasticity and electromagnetic theories. A unit normal vector is a vector with the length of 1. It points in the direction perpendicular to the surface. This vector is called a unit vector because its length is unity and normal because it is perpendicular to the surface, as shown here. The notion of the unit normal vector is central to the Gauss and Stokes theorem that we will introduce later in this lecture. By convention, the unit normal vector for a closed surface is taken to point outward, away from the volume enclosed by the surface. Some of the unit vectors for a sphere are shown here. Notice that the unit normal vectors at the Earth's north and south pole would point in opposite directions if the Earth were a perfect sphere. Now that we have introduced the scalar product and unit normal vector, the meaning of U dot n is clear. Basically, U dot n represents the component of the vector field that is perpendicular to the surface under consideration. Remember that the dot product between two vectors, such as U and n, is simply the projection of the first onto the second, multiplied by the magnitude of the second. Remember, also, that by the magnitude of the unit normal is 1. If theta equals 90 degrees, U is perpendicular to n, which means that the vector field is parallel to the surface, and U dot n is 0. So in this case, the component of U perpendicular to the surface is 0. If theta equals 0 degrees, U is parallel to n, which means that the vector field is perpendicular to the surface, and U dot n is equal to the magnitude of U. So in this case, the component of U is perpendicular to the surface, which is the entire length of U, and not just a component. Here we illustrate the projection of U onto the direction of N. Here is the definition in Cartesian coordinates of Nabla operator, also called del. It appears in the differential form of elastic and electromagnetic fundamental equations. This symbol represents a vector differential operator. Its presence instructs you to take derivatives of the quantity on which the operator is acting. The actions depend on the symbol following the del operator. For example, a dot will signify divergence, time will indicate curl, and no symbol following the del operator indicates gradient. Each of these operations will be discussed later in this lecture. Again, like all mathematical operators, del is an action waiting to happen, just as the square root symbol tells you to take the square root of anything that appears under its roof. Note that del is a symbolic vector. It does not contain any number. It can be characterized as a vector differential operator. Its presence instructs you to take derivatives of the quantity on which the operator is acting. Just like square root symbol, del, also known as nabla, is an action waiting to happen. We now introduce two new operators, gradient and divergence. The first is the gradient of a scalar field. Here is the definition of gradient in Cartesian coordinates. The gradient operates on a scalar field and produces a vector field that describes the rate of spatial change of the field at a point and the direction of steepest increase from that point. The gradient of scalar pressure field, for example, is defined as the gradient of P. Gradient of P represents the spatial rate of change of P. The z component of the gradient of P shows how fast the pressure changes in the z direction, and in the same way for the other coordinates. What does the vanishing gradient mean? If the gradient of P equals 0, then x0 is stationary point of the pressure. The pressure field could be a maximum or a summit, a minimum or a valley, or a saddle or pass. Note that the total differential theorem can be expressed in terms of gradient and scalar product. Now it's time for a quiz. Verify the gradient of the following scalar function. Verify the gradient of this following scalar function. Here is the divergence of a vector field U. It is an important new quantity. It is a scalar term, which here is defined in Cartesian coordinates. So the divergence of the vector field U is simply the change in its x component along the x-axis, plus the change in its y component along the y-axis, plus the change in its z component along the z-axis. Again, note that the divergence of a vector field is a scalar quantity. It has magnitude, but no direction. The divergence is important in many areas of physics and engineering, especially those concerned with the behavior of vector fields. In this quiz, calculate the divergence for the following vector fields. Here are your answers. The term divergence was first used by Oliver Heaviside for the same quantity with the opposite sign. Thus, positive divergence is associated with the flow of electric field lines away from positive charge. In this quiz, verify the divergence of the following vector. the divergence in the vector field here is increasing linearly with distance from the origin. Verify the divergence of this vector field. The divergence of this field is 0 at all points away from the origin. That is, divergence everywhere except at the source. So the reduced amplitude of the vector field, with distance from the origin, may compensate for the spreading out of the flow lines. Note also that this is true only for the case in which the amplitude of the vector field falls off as 1 over r squared. This case is especially relevant for the electrostatic. It describes the electric field of the positive point charge. The divergence of a vector field is a measure of how much the vector field spreads out or diverges from a point. In the case of fluid flow, the divergence at any point is a measure of the tendency of the flow vectors to diverge from that point. That is, to carry more material away from it than is brought toward it. In other words, divergence characterizes volume change. Thus, points of positive divergence are sources, faucets in situations involving fluid flow, or volume increase, while points of negative divergence are sinks, or drains in fluid flow, or decrease in volume. Let's now continue our discussion by describing the cross product in curl. The second kind of product is a vector product or cross product. It yields a vector. For two given vectors, A and B, the vector product can be written as follows. So vector C is the result of cross product of vectors A and B. It is defined as the determinants of a matrix, as defined here. The cross product of A and B is the magnitude of A times the magnitude of B times the sine of the angle between the two vectors. If A is parallel to B, the cross product is 0. As one application of the vector product, here is a calculation of the curl of U. Neither the divergence nor curl depends on the coordinate system in which they are computed. The curl is itself a vector and is here defined in Cartesian coordinates. Here's a quiz. Calculate the curl for the following vector fields. Here is your answer. The curls for all three vector fields are 0. Here's another quiz. Calculate the curl of this vector field. Here's your answer. This is a vortex, non-zero curl. Functions that tend to curl around have large curls. The curl of a vector field is a measure of how much vector field curls around a given point. In other words, it measures the vector field's tendency to circulate about a point, much like the divergence is a measure of the tendency of the field to flow away from a point. It will not affect the volume of material around a point, but the shape of materials around a point. Each component of the curl of the vector field indicates the tendency of the field to rotate in one of the coordinate planes. If the curl of the field at a point has a large x component, it means that the field has significant circulation about that point in the yz plane. The overall direction of the curl represents the axis about which the rotation is greatest, with the sense of the rotation given by the right-hand rule. The curl operates on a vector field and produces a vector result that indicates the tendency of the field to circulate around a point in the direction of the axis of greatest circulation. Kronecker and Levi-Civita are two important tensors for elastic and EM studies. The symmetric unit tensor of rank 2, the Kronecker tensor, is defined as delta ij is equal to 1, when I is equal to j, and 0 when I is different from j. Levi-Civita tensor is an antisymmetrical unit tensor. It is important in the mathematical description involving cross products like Maxwell's equation. The Levi-Civita symbol is defined here. Note also that the value of Levi-Civita is equal to 0 if any two of the indices are repeated. The Levi-Civita symbol describes a third-order antisymmetric tensor because the value of Levi-Civita changes sign if any two of the indices are interchanged. If we denote by the curl of U by D, we can rewrite the curl of U with Levi-Civita symbols as follows. For reasons which will become evident in our definition of Maxwell's equations, we introduce the subscript notation for tensors of rank higher than 0 and the summation convention. In subscript notation, a vector E can be noted by EI, where lowercase Latin subscripts, for example I, are employed. They take the values 1, 2, and 3. Here is another example of subscript notation. This notation permits us to write many of the formulae in seismology in a much shorter form than would otherwise be possible, making these formulae easier to remember and to understand once the notation is learned. Here's one more example, where delta ij is Kronecker delta function. Many EM formulae require a summation over all values of the subscripts. The summation convention states that whenever the same letter subscript occurs twice in a term, that subscript is to be given all possible values and the results added. For example, the scalar product can be written as follows. The summation symbol may then be omitted because the repeated subscript indicates the summation. Here's one more example, or cross product. We can omit the two summation symbols. The subscripts j and k are repeated here, and therefore they indicate summations over j and k. However, there is no summation over I. So the summation convention dispenses with writing summation signs, leaving the summation implicit. Any repeated index symbol is summed over. If the index I is used twice in a given term of a tensor expression, it means that the term is to be summed for all I. Several distinct pairs of indices may be summed this way. For three given vectors, A, B, and C, the following properties hold. Note that the last operator here, nabla squared, is known as a Laplacian. Here is an identity that we will use again and again in these lectures. The curl of the gradient of any twice differentiable scalar field is always the zero vector. The divergence of the curl of any vector field is always 0. Here's a quiz. Verify the Laplacian of the following scalar function. Let's conclude this lecture by describing the Gauss and Stokes theorems. Here is the configuration for the description of Gauss and Stokes theorems. D indicates the volume. Partial D indicates the surface around the volume. And C indicates one circulation line of this surface. We consider a 3D model, D, bounded by a closed surface, partial D. If W is defined in D, the divergence theorem states that in D, the volume integral of the divergence of W is equal to the surface integral of the scalar product of W and the normal vector to the surface of D. Here is Gauss' theorem, not to be confused with Gauss' law that we will introduce in the electromagnetic classes. On your left, you have a volume integral, and your right, you have surface integral. N is a unit vector with direction perpendicular to the surface. If the surface is closed, forming a balloon, N is outward, is positive. Defining two scalar fields, U and V, provided that their first and second derivatives exist, we can deduce the following relationship from the divergence theorem. This relationship can be derived from the divergence theorem by using this definition of W. In that, a similar type of theorem to divergence, due to Stokes, states that for any vector field W, we have this relationship. Here we use the curl of vector W instead of divergence of W, whereas the divergence theorem relates a surface integral to a volume integral. Stokes' theorem relates a line integral to a surface integral. The circulation of a vector field over a closed path C is equal to the integral of the normal component of the curl of that field over a surface S for which C is a boundary. The circulation of a vector field is a line integral around a closed loop. Remember, there is a large selection of iMode education lectures which can further enhance your knowledge of wave propagation, elasticity, electromagnetism, wave field sampling, wave field decomposition, and imaging. Thank you for listening to this iMode education lecture.